right? So I'm going to talk about topological phases of matter, sort of generally. You know, my main purpose here is to just sort of convey some intuition and some physical motivation for the kinds of mathematical structures that are used for describing topological phases. Okay, so I'm going to give you a rough framework or a rough outline of this in the next lecture. So roughly today, what I plan to do is to introduce a certain sort of intimidating sounding mathematical framework called category theory. And to show you how this mathematical framework sort of very naturally describes topological phases. Okay, so you know, the rough analogy is you know, if you want to talk about sort of conventional phases of matter, which are classified on the basis of symmetry groups and symmetry breaking, you have various different phases of matter which can break various different symmetries. Well, the mathematical framework that's used to understand those phases is basically group theory, right? Group theory is what underlies the Ginzburg-Landau formulation of phases and phase transitions. And so, you know, the basic objects are groups. So different phases, you know, roughly correspond to different unbroken subgroups, right? So you know, different phases are characterized by different order parameters, and the way you know that they're different is because they leave different subgroups invariant. You might have a phase that breaks no symmetry and leaves the entire group invariant. You know, leaves the entire group unbroken, or you might have a phase that breaks some of the symmetry and has some subgroup unbroken, or you might have a phase which breaks all of the symmetry. But the things that are attached to phases are basically groups, symmetry groups, the unbroken symmetry group. For topological phases, it turns out that this kind of conventional framework is not really the most convenient thing, the most convenient one for describing different phases and you know, attaching different invariants to different phases. And instead, the really natural mathematical framework is category theory. Okay, so different phases, different topological phases turn out to be best characterized by different categories. So I'll tell you sort of, you know, roughly what a category is, sort of describe what kind of mathematical structure it forms. In particular, it's not just a single it's not just a general category that describes a phase, but it's a very specific kind of category. So there'll be something called a unitary modular tensor category, and I'll you know, this is not a math lecture, so I'm not going to give you theorem definition proof. But what I will do is sort of tell you what each of these words means, at least at a physical level. So each of these words sort of characterizes the kind of category that you have for describing your topological phase. So I'll tell you, roughly what these words mean and how you get them from physical assumptions. Okay. So that's going to be the thing that I'll talk about today. And the second lecture tomorrow, I'm going to talk about an additional ingredient, which is that of symmetry. Okay. Global symmetries. So today there will be no global symmetries involved. Okay. So that in a way sort of makes it easier. And this might seem a little bit backwards, right? Because typically we're used to thinking about sort of symmetry-based distinctions between phases as sort of the natural thing to do, and then topological phases, topological order is some sort of additional ingredient beyond that. But really, what I'll try to argue is that a more fundamental way of thinking about things is first you want to understand the problem without symmetry. So think about topological phases without symmetry, and then this is sort of the appropriate framework, and then add symmetry as sort of an additional constraint on top of that. So it turns out that category theory provides you with a way of distinguishing among different topological phases. Then when you add symmetry So you impose the constraint that your Hamiltonians are invariant under a certain symmetry. That sort of gives you a refined understanding of the various phases you can have. And then that actually sort of really gives you sort of a whole plethora of different phases. You can have the usual symmetry breaking versus not symmetry breaking phases. But then when you have a topological phase with symmetry, then the topology, the various topological excitations can interplay in all sorts of complicated ways with the symmetry. So I'll try to discuss that tomorrow. But for today, we're just going to focus on this. Okay. Oh, and also please feel free to interrupt with questions whenever you have them. Yeah, great, awesome, great. Okay, so. I saw the previous lecture. I guess it was Mike Zalatel, so he might have already introduced some of these concepts. But just so we're all on the same page, I'm going to introduce the basic framework for studying these topological phases. I'm going to tell you first what kind of Hilbert spaces we'll be working with. Right? This is quantum mechanics. It's many-body quantum mechanics, so there'll be a Hilbert space, and then I'll tell you something about the kinds of Hamiltonians that we'll look at. So first thing is the Hilbert space. So this is not necessary to think about it this way, but the way I like to think about these Hilbert spaces is I want to think of all these different topological phases as sitting in an underlying lattice model. Some kind of a generalized spin model. So what I mean by that is just that I have a lattice made out of sites, and to each site I attach a finite dimensional site Hilbert space. For example, something like an icing model where I have 2 states per site. So then it's a 2-dimensional Hilbert space per site. So the Hilbert space of the many-body system is just a tensor product over all sites, which I'll call, just give them a label, J, Hj. Could be a 1D lattice, could be, well, today, in 1D it turns out that as far as topological phases without symmetry, not much interesting happens. So today, most of the lattices, pretty much all the lattices we'll be interested in will be 2-dimensional. Okay, so this is a tensor product over all sites J of a 2-dimensional lattice. So just label all the sites in a 2-dimensional lattice, assign site Hilbert spaces Hj to them, take the tensor product. Okay, so just as an example, if I had, I'm not going to draw an entire 2-dimensional lattice, but let's say that I had, I'll just draw 3 lattice sites. So just as an example, I could have a spin 1/2 system. Okay, so a spin 1/2 system, each lattice site has 2 states up and down, and so a state in the tensor product. Well, there are 8 different states in the tensor product. They correspond to all possible configurations of up and down spins. Okay, so a general state psi inside this tensor product, would be some kind of a linear combination of these 8 states. So I don't know. There'll be some kind of amplitude assigned to the up state. So this is how you represent states in a tensor product, right? If I take a tensor product of 3 different site Hilbert spaces, I have 3 different choices for each spin. So I just write it this way, plus dot dot dot. So there's 8 more terms there. Okay, so one thing you can notice, from just the way that I sort of started writing out this state, even just for 3 sites, is that this is not, this is working with the full Hilbert space is not very easy, right? There's exponentially many states in the full Hilbert space. There's the dimension of the site Hilbert space to the number of sites, which grows exponentially with system size. So, so generally, you don't want to work with sort of individual states in the Hilbert space. You want to sort of think about individual states in the Hilbert space. They're sort of there, and you can manipulate them, but when you actually probe them, you don't want to sort of look at the whole state. So what you want to do instead is look at a very useful construct for sort of measuring or probing different states is this idea of a reduced density matrix, which I think, judging from what was written here before, Mike already talked about, but I'll sort of very quickly describe. Okay, so reduced density matrix. Okay, so the idea is we have a many-body system. It lives on some lattice, and I have some state in the many-body Hilbert space of this system. But maybe I don't care about the whole state. Maybe I only care about sort of information in the state that's contained within some local region A. We call it A of spins. Okay, maybe that's all I care about. So then, if that's all I care about, then I shouldn't have to work with the full state in the many-body Hilbert space. I should somehow be able to understand, what the local piece of it on A is. Okay, but the problem is, in general, states are entangled, right? So if I just give you a configuration of spins, I have a spin system and I just choose a configuration of spins, then it certainly makes sense to just restrict that configuration to the region A. Right? That's sort of a classical picture. But quantum mechanically, we can't do that because quantum mechanically, there will be some correlations in the state. Our state is not some kind of a classical configuration that we can just sort of truncate. So we can't do the truncation naively, but it turns out that you could still truncate if you sort of keep track of all these correlations. And this is what a reduced density matrix does for you. Okay, so the formal definition of the reduced density matrix is that the reduced density matrix on A, on the region A, which sort of tells you everything about the region A, is so let me call, this is region A. Let me call everything else A complement, A bar. Okay, so the reduced density matrix, on region A is just start with. Okay, so the reduced density matrix is always associated to a state psi. So what you want to do is you want to make this bracket combination, and you want to trace out all the degrees of freedom in the complement. Okay, and mathematically, what does this mean? Just to give an explicit formula. Well, mathematically, the way this is really explicitly just a trace. So mathematically, what you want to do is think about the whole Hilbert space of the system. Remember, it's this tensor product over sites, over all the sites of the system. So I can sort of look at each site as being in either A or A complement, and I can write the whole Hilbert space as the Hilbert space associated to A, tensored with the Hilbert space associated to A complement. Okay, so these are configurations on A. These are configurations on A complement. Okay, and any state psi can be decomposed with respect to this tensor product. All you have to do is pick a basis, let's say a basis of configurations on A, pick a basis of configurations on A bar, and any state psi can be decomposed as some kind of linear superposition of tensor products of these configurations. Okay, so it's sum over alpha and beta, where alpha is sort of an index that that runs over the basis of configurations of A, and beta is an index that runs over the configurations of A complement, and it's some general superposition. So there's some general coefficients C alpha beta. Psi A alpha tensored with psi A bar beta. Okay, so psi A alpha are the states that form the basis of HA, and psi A bar beta are the states that form the basis of HA bar. And there's some kind of normalization condition, sum of mod squared of these coefficients equal to 1, just to have a normalized state. So when you write your state this way, then it's sort of meaningful to take to trace out a complement. Okay, so what it really means is just explicitly take this form of psi, plug it into this equation. What do you get? You get a formula that looks kind of ugly, but it's not so bad. So trace a bar of, okay, so I have a bra copy of psi, and I have a ket copy of psi. So I have sort of two copies of this guy that, you know, they're related by complex conjugation. So to make two copies of this guy and multiply them out together, I'm going to have a sum on alpha beta and another set of indices alpha prime beta prime. You know, the two sets of indices correspond to the fact that you have two different copies of psi. And I'm going to have a coefficient C alpha beta from the bra and C alpha prime beta prime complex conjugate from taking the ket. And I have psi A alpha psi A bar beta. And then from the bra vector, I have psi A bar beta prime, psi A alpha prime. Okay, so this looks like a complicated expression, but it's not. It's not once you trace out a complement. So what does it mean to trace out a complement? Well, it literally means, you know, focus on this piece of this equation. Okay, so this is a bra-ket combination entirely on a bar. So you just think of it as an operator on a bar and take its trace. Okay, how do you take the trace of an operator? Well, all you do is, you know, this is sort of the basis on a bar, you know, indexed by this index beta. So just think about this thing as a matrix in you know, written out in this explicit basis. So this is a very simple matrix. It's just a matrix with the non-zero entry and the row beta, column beta prime. Everything else is zero, right? Because you project onto beta prime, and then you map that state to beta. Okay, so this is a very simple matrix. It just has 1 in row beta, column beta prime, and zeros everywhere else. Okay, so its trace is either 0 or 1, and it's 1 precisely when beta is equal to beta prime. Okay, so to take this trace, all you have to do is just set beta equal to beta prime and do the sum. Okay, so this is very explicitly sum on alpha, alpha prime, and beta, because we set beta equal to beta prime, C alpha beta, C alpha prime beta. Just set beta prime equal to beta everywhere in this equation. And we've already taken the trace of this, so it's gone. Psi A alpha, psi A alpha prime. Okay, that's it. So this is the formal definition of a reduced density matrix. Okay, so this reduced density matrix lives entirely in the Hilbert space on system A, right? It's only made out of these basis states, which are basis states on A. B has been traced out. B is gone. I don't need to think about B anymore. Okay, and furthermore, it's in general a mixed state, right? So even if you start with a pure state, like in this case we started with a pure state psi. What we ended up with is something like this, with, you know, potentially many different non-zero coefficients. Okay, so this is in general a mixed state. And okay, so let's see. Do I have another board? Oh, perfect. Okay, so that's the definition of a reduced density matrix. Why is that a useful concept at all? I just sort of, you know, pulled it out of thin air, it seems like. So the important thing about a reduced density matrix is it basically characterizes all the information that's available to you about the state psi if you only do measurements on the spins in region A. Okay, so the key property of the reduced density matrix is that it reproduces all the correlations in A. So if I take X to be an operator made out of spin operators that act only on the spins in A. Okay, so I'll just call that an operator in A. Okay, so formally mathematically, what I mean by that is that X, if you think about it with respect to this decomposition of Hilbert space on A, Hilbert space on A complement, is that X is some operator XA which acts on the HA Hilbert space, and then tensored with the identity in the complement. So it does nothing on the complement, just sort of whatever configuration, whatever state you have on the complement of A, it just does nothing, acts like 1, just does nothing to that state. But on the state in A, it can do something. Okay, so this is what it means to have an operator that acts in A. So this is just an operator made out of spin operators in A. So the key property of the reduced density matrix is that for any such operator which acts only in A, the expectation value of this operator in the state psi. Okay, so the expectation value of this operator X in this global state psi in this many-body Hilbert space can be obtained. This expectation value can be obtained as it can be obtained just from the reduced density matrix. So just by tracing XA, sort of, this XA against rho. Okay. So remember, X can be any operator. So this isn't just sort of a single operator acting on a single spin. This could be like, if A is a sufficiently big region, it could be like a 2-point correlation function of spin operators, which correspond to 2 different spins within A, or a 3-point correlation function, or whatever. It doesn't matter. Okay. So any correlation function of any operators that live entirely inside A, you can get from knowing the reduced density matrix rho in that region A. So for really rho, you want to think of it as sort of characterizing everything you can possibly know about the state on A. Okay, and this will be a very useful concept for characterizing topological order, it turns out. Okay, so far I just talked about the Hilbert space, right? I haven't said anything about the dynamics yet. So let me now talk a little bit about the kinds of Hamiltonians we're going to deal with that give us topological order. Okay, so what kind of Hamiltonian do we have? Hamiltonian. Okay, so basically we're going to be dealing with local Hamiltonians. Okay, so Hamiltonian H is an operator that acts on the many-body Hilbert space, and it's local in the sense that it can be written as a sum of local terms. So sum on, I'll call it some index x, which you can think of as roughly as corresponding to positions, different physical locations in your lattice, of terms hx. Okay, and the point is that each hx has to be a local term. Okay, so each hx is local in the sense that hx is equal to some operator, well, let me call it A. Actually, A is a bad term. Let me call it Y. Y sub x tensored the identity, where Y sub x only acts in some local region around. Let me pretend that x index the different sites of the system. So Y sub x is some operator which only acts non-trivially, only acts within some local region, some finite, let's say, disk of radius r around this region x. Okay, so the physical picture is I have, my lattice. I'm not going to draw the lattice. It's some okay, it's a caricature of a lattice. And so the physical picture is that, I have some site x, and then this operator y sub x can only act on the spins within a radius r of this site of this center x. Okay. On the rest of the spins outside this disk, you just act as the identity. Okay, so this is a local operator acting near x, and r is a parameter that sort of characterizes the kinds of Hamiltonians that you look at. How local are they? Well, they're local with local range r. So this is a definition of strict locality. In many physical applications, you want to relax this condition of strict locality and allow for exponentially decaying interactions. That's sort of extremely natural. So that's something you can do. Everything that I say today goes through for any Hamiltonian with sufficiently fast decaying interaction. So they don't have to be strictly local, but let me just assume strict locality for now because it's easier to deal with. Okay. Right. Another technical assumption that one has to make is that each of these local terms has bounded strength. Okay, you don't want to sort of deal with the situation where you can have sort of arbitrarily large terms. So each of these terms has bounded strength. Now, how do you measure the strength of a local operator, or any operator for that matter? Well, the most natural thing to use is the operator norm. So this is something called operator norm, which is just the absolute value of the largest eigenvalue. Okay, so I'm going to assume that the operator norm of all these local pieces is bounded by some j. So j is sort of the natural, when people say energy scale of the problem, j is the natural energy scale of the problem. Okay, j has units of energy. This goes into building a Hamiltonian. And I'm going to assume that all my local terms are bounded by j. So that's saying that j is the natural scale of the problem. Okay, so that's a second parameter that characterizes the class of Hamiltonians we want to look at. The first one was R, which characterized the locality property of the Hamiltonian, how local it is. J characterizes the energy scale of the Hamiltonian. And then there's one more, sort of the most important characteristic of these Hamiltonians is that they're going to be gapped. Okay, so what that means is that there's an energy gap between the ground state. Okay, so I'm drawing sort of a spectrum of this many-body Hamiltonian, so it's some horribly complicated thing, and I really know very little about it. But what I do know, or what I demand to be true, is that there's a ground state with energy. Let me call it E0. And then there's a gap. So this is greater or equal to some number delta, which is going to be the third parameter in the problem, to the first excited state E1. Okay, and then there's some horrible excited state spectrum, which I really know very little about. But I'm going to demand this. Okay, so to make this precise, I'm just sort of giving you a very rough overview. So to make this precise takes quite a bit of work. So in particular, you really have to be talking about the thermodynamic limit, right? Because any generic system in a finite dimensional Hilbert space will have gaps between all states. So there's always a gap. There's always a so-called finite size gap. So what we really mean, or what we really demand by making this gap assumption is that this gap stays open in the thermodynamic limit. Okay, so we demand that the energy difference between the ground state and the first excited state is greater or equal to delta always, even in the thermodynamic limit. So in other words, this gap doesn't close as you put in more states. You go to the thermodynamic limit, you make your Hilbert space larger, you sort of introduce more and more states. You don't want this gap to come crashing down. You want it to stay open. Okay. Right. So this is sort of really the key technical assumption. It turns out that this assumption of a gap is really what lets us sort of isolate interesting phenomena happening close to the ground state. Okay, so when we study topological phases, for us, we're always going to be basically interested in the ground state. It's really physics of the ground state. Okay, so we're always going to be at temperatures low enough, sort of much lower than delta, so that we're really always in the ground state, or at least very close to the ground state, maybe sort of finitely many excitations above the ground state. Okay, so studying topological phases is studying physics of the ground state, and you might think that that's really boring. I mean, when I say gapped system, the natural thing that might come into your mind is something like an insulator, right? An insulator has a gap between the ground state and excited states, and that you think of as completely boring, right? Like you can think of an insulator in the atomic limit where you just have filled electronic orbitals on each side of a lattice. And that's sort of the most boring state imaginable. It's just the tensor product state, and nothing is happening. Everything sort of just sits in one place. But it turns out, and so this is sort of the whole point of topological phases, is there are interesting insulators, or more generally just gapped systems if you don't have a conserved charge, that are not adiabatically connected to sort of that boring atomic limit tensor product state insulator. Okay, they're sort of very far away from anything that resembles that. If you want to try to change parameters and continuously deform your Hamiltonian to something that does give you a trivial atomic insulator, you always encounter a phase transition. Okay, so typically the fact that that you always encounter a phase transition in this way, that this really these topological phases really form a separate phase, that's usually reflected in some very exotic properties of the system that happen at low energies. Okay, so like for instance, you can have degeneracies. So if you have a system on a topologically trivial manifold, like a sphere, for instance, I mean, experimentally it's very hard to imagine putting a system on a sphere, but just as a thought experiment, you could. There might be a unique ground state, but if once you put it on a torus, there might be a ground state degeneracy. Okay, and that's a hallmark of a topological phase. That's not something you could ever get in a trivial atomic insulator, but that turns out to be sort of a characteristic property of topological phases. Okay. Okay, good. So I've talked about the Hilbert space, the kinds of Hilbert spaces we'll be working with. I've talked about the kinds of Hamiltonians we'll be working with. I have told you that they're basically very roughly described by sort of three parameters, or the families of Hamiltonians we're looking at are described by three parameters. R, J, and delta. Let me just write them out here. So this was the range of interactions. That tells you how local the Hamiltonian is. This is the strength of the interactions. And this is the gap. Okay. So this is a nice class of Hamiltonians to look at. All the interactions are bounded in range, they're bounded in strength, and there's a gap that stays open in everything. From now on, those are the kinds of Hamiltonians we're looking at. Okay. Good. I guess I can't really raise this, so that's okay. By the way, I started at what time? 3:40? 3:45?
Yeah, it would have been a little past 3:40.
Okay, 3:45, let's say. Okay, so I'll go till 4:45. So I'll go for another 17 minutes. Okay, good. So, okay, so what can we do with, I gave you definitions, of the class of Hamiltonians we're working with. What can we do with these definitions? So, I'm not going to precisely prove anything, obviously, in this lecture, but let me just tell you that sort of the main consequence of having a gap Okay, having the gap is really the key technical assumption. It's sort of what allows you to move forward, and physically that makes sense because it sort of isolates low energy phenomena. The way that you can get at that technically is through the existence of a correlation length. So it turns out that the existence of a gap implies that there's a natural length scale in the problem. Okay, I mean there's already a natural length scale which is the lattice spacing, but the existence of a gap means that there's another length scale, psi, which is called the correlation length. So this you typically think of as being, some number of lattice spacings. Okay, and in a gapped system, the point is that the correlation length is finite. Okay, so it can become infinite once you close the gap and approach criticality, but if the gap stays open, the correlation length stays finite. Okay, and the way that the correlation length appears is that if I take two observables x and y that are physically separated, so x might act on a spin here, maybe a couple of spins, a cluster of spins here, and y act somewhere, some distance r away, then the main consequence of the gap is that this connected correlation function decays exponentially. So it's bounded by some constant, I guess depends on the operators x and y in question. But then there's an exponential decay, e to the minus distance between x and y over xi. Okay. So that's correlations between operators die off. Okay. Now, a restatement, or actually it's not exactly a restatement, but sort of an alternative way of thinking about this correlation length is, instead of thinking about just correlation functions this is an implicit state here, and it's we want to think of it as the ground state of some Hamiltonian. But instead of thinking about correlation functions in the ground state of some Hamiltonian, what you can do, another way you can think about sort of the effect of this correlation length is in terms of changes that you can make to the Hamiltonian. Okay, so this is a particularly useful way of thinking about things. So so just as an illustration, one thing you can do is perhaps change the Hamiltonian in some region of spins, and then see what effect that has far away. Okay, so you sort of hit the system there. Just change the Hamiltonian, change the interactions, and what effect does that have far away? You can ask, what effect does that have far away? Okay, so let me call this, let's say, region A. And let's say that I have some operator x of A that's built out of spins that are all in region A that are far away from where you make this perturbation. So this distance is r. Okay, so right. So what I mean precisely, I'm now introducing a perturbation to the Hamiltonian. So there's not a single state involved. There's two states. So there's the original ground state, which is the ground state of the original Hamiltonian H, and then something I'll call psi prime, which is the new ground state, which is the ground state of H with the perturbation, H plus delta H. Okay, so in a gapped system, in a system with a finite correlation length, you really expect that changing the Hamiltonian out here shouldn't affect things there, right? Certainly, if this change delta H is small, you can sort of re-express. You do perturbation theory and you express this thing in terms of correlation functions. But in general, even if you make a large change here, as long as you make that change far away, you change some couplings, you flip the sign of some couplings, whatever, you make even a large change, it really shouldn't affect things here as long as as long as R, the separation is much larger than the correlation length. Okay, so the statement would be that the expectation value of your observable XA in the ground state, in the new ground state psi prime, should be approximately equal to the expectation value in the old ground state. Okay, nothing should have changed far away. So the perturbed expectation value should be roughly equal to the original expectation value plus, a correction of order e to the minus r over xi. That's it. That's the change you expect. And since I introduced this idea of a density matrix that encodes all correlations, a way of rewriting the statement that's sort of independent on the kinds of observed, this should be true for all observables that are localized within A. So really, it's a statement about the density matrix on A. So really, the statement is that the density matrix on A that's built out of this new perturbed ground state should be pretty much equal to the density matrix, the old density matrix made out of the original ground state, plus a correction of size e to the minus r over xi. Okay. So this is sort of a very natural intuition to have. Now, the surprising thing, okay, so certainly something like this is true in the trivial gap state, like a trivial insulator in the atomic limit. A trivial insulator in the atomic limit is, okay, trivial spin system, let's say, is something where all the sites are decoupled, so none of the sites are talking to each other. Okay, so in that case, obviously, anything you do here is not going to be detectable here. The system is just not talking at all. But the surprising thing is that this intuition actually fails for topological phases. Okay, so for topological phases, this intuition is false, but it fails in a sort of very topologically non-trivial way. Okay, so for this kind of setup, it turns out that it is true, but if you sort of choose your region A in a sufficiently funny, topologically non-trivial way, then it turns out that this can fail. Okay, and this is, I think, the most sort of direct way of understanding why these things are called topological phases, because you really see how the topology comes into the problem. Okay, so let me flesh that out a little bit. Okay. Okay, so let me flesh that out a little bit. Let me consider, again, let's say we're in 2 dimensions. I have a Hamiltonian. I'm going to make a perturbation, and I'm going to make a perturbation in some region. And for technical reasons, it turns out that I have to sort of make a perturbation not just in one sort of spatially localized region, but 2. So 2 small regions. Some cluster of spins here, delta H1, some cluster of spins here, delta H2. Okay, so that really shouldn't change things. I mean, okay, as long as I'm looking at regions A that are far away from both the location of perturbation 1 and perturbation 2, nothing should really change about the density matrix. And that's true if the region A is a topologically trivial region. So if the region A is a disk-like region, then that statement is still true. Your sort of trivial intuition still holds. But something funny happens if I take A to be a topologically non-trivial region. So I'll take A to be this kind of annulus. Okay, so A is sort of everything that's inside this annulus. That's A. That's my region A. So A is still very far away from both delta H1 and delta H2. I can sort of, as long as these 2 perturbations are well separated spatially, I can ensure that this thin annulus sort of stays far away from delta H1, delta H2. However, now it is not the case that these 2 density matrices, rho A prime and rho A, so the density matrix for the unperturbed and the perturbed system, it's no longer true that they're similar. In fact, now in a topological phase, what can happen is that rho A and rho A prime are very far away from each other. They're actually orthogonal in an appropriate sense. Okay, so in other words, rho A is very, very different from rho A prime. Okay, so for the experts in the audience, the intuition here is that if you've seen topological phases before, you might have heard that they're described as deconfined phases of gauge theories. And what's really happening here is that this perturbation, delta H1, well, these perturbations together, but in particular, delta H1 is localizing some kind of a gauge charge. It's trapping some kind of a gauge charge in here. And this gauge charge, even though it's sort of not detectable in any local measurements in disk-like regions, it can be detected if you make a measurement in an annular region like this, basically because of Gauss's law. You can sort of, if you allow yourself access to all correlation functions, all the information in A, you can kind of, you can kind of see how much charge is being trapped just through an ordinary Gauss's law measurement. You just sort of measure the total gauge charge that you measure the electric field that this gauge charge is producing. That tells you about the gauge charge. Okay, so by varying this this perturbation here, delta H1, which think about it as some kind of a potential which tends to either attract or repel a gauge charge, you can go from a situation of not having gauge charge to having gauge charge in your lowest energy state, and that can be actually detected far away. Okay. Good. So this might seem very weird. So it's nice to have a specific, exactly solved model of this. Now, did Mike or anybody actually today talk about the toric code?
No.
Okay, great. So in the last 5 minutes, I'm just going to write down the toric code because that's sort of the simplest example of a of a system where this intuition is borne out, where you have precisely this happening. So I'm going to start here. So toric code is sort of the prototypical example of a topologically ordered phase. It's very nice because it's exactly solvable. I'll solve it right on the board, more or less. It's analytically solvable, and it displays these sort of exotic properties. It's a finely tuned model. It's not a model that is easy to realize in nature, but for the purposes of illustration, it's great. So, great. What's the toric code? So it's like everything I've been discussing today, a spin model. So I have spins. So first of all, I have a lattice, which I'm going to take to be a square lattice. And I have spins, and one strange thing is that the spins are going to live on the links rather than the sites of this lattice. Okay, so the spins, and they're going to be spin 1/2 degrees of freedom, live on all the dots that I've drawn. Okay, so all these dots contain spin 1/2 degrees of freedom. Okay, so there's a spin 1/2 degree of freedom per link, and this is already sort of, if you're familiar with gauge theory or lattice gauge theory, this is sort of already looking like lattice gauge theory, because in lattice gauge theory you have variables, basically vector potentials that are defined on links of a lattice. So this is sort of the simplest example of a lattice gauge theory, or comes from the simplest example of a lattice gauge theory. Right. So those are the degrees of freedom, spin 1/2 living on the links of a square lattice. Now, as far as the Hamiltonian H is made out of two kinds of terms. There's a conventional minus sign, so there's a sum over vertices V. So a vertex looks like this, vertices V of the square lattice, and there are some terms A sub V, which I'll write down just below. So there's a bunch of terms, each associated with the vertex of the square lattice, and then there's a sum over plaquettes P. So there's the squares, and there's a term associated with the plaquette P. And these terms are very easy to write down. I'll just do that explicitly. So A sub V, the term associated with any vertex V, is just the product over all 4 links L that terminate at V. So in other words, for this vertex V, it will be the product over these 4 links here that make this star shape, that adjoin V. And on each such link, I'm going to, on each such link, I have a spin 1/2, so I'm going to act with a Pauli sigma matrix. So I'm going to act with Pauli sigma, sigma X operator on link L. Okay, so it's a product over all links L of Pauli sigma x acting on the corresponding link. So sigma x, sigma x, sigma x, sigma x. That's what this operator does. BP, on the other hand, is sort of a dual to this. It's defined on squares rather than vertices, and it's a product over all links L, all 4 links. Again, it's 4 links that border this plaquette P. So 1, 2, 3, 4, and you act with sigma z. Okay. So the Pauli sigma z matrix. Okay, so these guys anti-commute. The sigma x rather than the sigma z anti-commute. Okay, so what can you tell about this Hamiltonian? So one thing that you can tell is that, which makes it very easy to solve, is that all these terms commute. Okay, certainly all the A's commute among each other because they're all made out of sigma x operators, and sigma x operators all commute. Doesn't matter on the same side, different site. All sigma x are commute. The only anti-commutation is between a sigma x and a sigma z on the same link rather. Similarly, all the BB's commute because they're all made out of sigma z's. The only potential issue, the only potential place where these terms might fail to commute is, you might think that some of these A's might anti-commute with some of these B's, right? They might fail to commute with some of these B's because the A's have sigma x's and the B's have sigma z's. So if I have a sigma x trying to commute with a sigma z, I get a minus sign, right? They anti-commute. So that you might think that that's a problem, but it turns out that due to the geometry of this lattice, it's never a problem. So if I take you might imagine that if the plaquette P starts sort of being close to overlapping with the vertex V, like let me take plaquette P to be here, vertex V to be here, then B sub P might not commute with A sub V. But it turns out that what happens is, you would be right, there is some anti-commutation going on. There are basically 2 links, there's this link and there's this link that the plaquette and the vertex have in common. And there's sort of a miracle that happens, which is you get a minus sign from each of those links, but because there's precisely 2 links, that minus sign cancels, and these terms commute. Okay, so all these terms commute. So all A sub V, B sub P commute among each other. Okay. So that's nice. So what that means is that there's when you have a Hamiltonian that's filled out of commuting terms, it's basically very easy to solve it because the fact that all these things that make up the Hamiltonian commute means that there's a common basis of eigenstates for all these terms, A sub V and B sub P and H. Okay, so once you find that eigenbasis of states, and you work in that eigenbasis of states, the problem becomes very easy. Like not only is the Hamiltonian diagonal, but every single term in the Hamiltonian is diagonal. Okay, so in particular, all these terms A sub V and B sub P, because they're made out of sort of disjoint Pauli matrices, they all have eigenvalues plus or minus 1. So if I can just find this common eigenbasis of these A's and B's, find an eigenstate within this eigenbasis, which is, the way I've written things, plus 1 eigenstate of all the A's and all the B's, then that's automatically the ground state. That's automatically the lowest energy state, right? Because the lowest energy state can basically only get whatever minus the number of vertices minus the number of plaquettes. That's the lowest you can possibly go. That's the lowest state in the spectrum. So if I find a state or all the states that satisfy that, then I will have found my ground state spectrum. And then I can play these games and sort of, see what happens when I start perturbing the Hamiltonian. So that's going to be the subject of, I guess, tomorrow's lecture. But yeah, let me cut it off here just because I'm running over time. Thanks.